Okay, power functions. By power functions, I'm talking about functions that look like this. Y equals to some constant times x to some power. An example of such would be y equals to 2x cubed. How's that? Yeah. Our goal is to understand the generic shape of these power functions. But before I do that, I also want to explain a little difference between a power function and an exponential function. An exponential function looks like a times some b to the x power, something like this. And an example of such would be y equals to 3 times 2 to the x power, something like that. Okay? And what I'm trying to say is that look at where the x is. If x is in the exponent, what do you call this? You call this an exponential function. If x is in the base and there's some power given, which is a fixed power, the power is fixed, then you call this a power function. Okay? Now, they have completely different behavior. For example, if you drew the graph, this exponential function, we're going to learn exponential function graphs later, so you don't have to know this at this point, but if you drew the graph, it goes something like that. Whereas this one, if you drew it, it's more like this. Okay. So their shape is completely different. The biggest difference between the two is that this thing never becomes negative. 2 to some power never becomes negative, but this does become negative. Okay. All right. So let's try with the simplest one. Y equals to x squared, y equals to x cubed, y equals to x to the fourth. What's that? Okay. Y equal to x squared, you'll know that it's a parabola. Y equal to x cubed. This was also given as one of the basic graphs that you have to know. Y equals to x to the fourth is just like this parabola, but it's like somewhat flat in the middle. It's like, yeah. So if this was like the pencil lead, tip of the pencil lead, this would be what the pencil lead would look like after you used it a lot. Okay. Now y equals to x to the fifth again looks like x cubed, but it's flatter in the middle. And as you go higher, every time you get an even power, so y equals to x to the sixth, this is an even number, right? You get another of these parabola, but the difference is that it gets flatter and flatter. The middle point becomes more and more flat. Okay, so here's what you get if you put this, all of them together. So let's put them all together. So here's 1, 1, and here's -1 and 1. So first, y equal to x squared would be like this. This y equals x squared. Y equals to x to the fourth will be, maybe I'm going to use red. This will be y equals x to the fourth. I only have red and black, so again I have to use the black one. If you have y equals to x to the sixth, then it'll be even more flat in the middle. Go up very fast. So that's your y equals to x to the sixth. So you get the idea, right? Yeah. They all look pretty much the same, but their flatness in the middle is different. And these functions, when you have even powers, the graph is always symmetric with respect to the y-axis. And if any function is symmetric with the y-axis, we call them even functions, because all of these, for at least for the polynomials, they have even powers. Okay, so such a function is called an even function. And we can summarize by this hand sign that if you have even function, what does their shape look like? Like this. Okay, yeah. So you have to remember even functions like that. Okay. Now, on the other hand, if you put this and this together, erase this. Y equals to x cubed will be like this. And y equals to x to the fifth would be, if this is 1 and 1, be like that. And then it's going to hit the 0 before, and then it's going to go like that. So it stays near the x-axis more. Okay, so this is your y equals to x to the fifth. And again, if you draw the graph of x to the seventh, eighth, and all that, these all look like this. Just the difference is their flatness in the middle. And the symmetry that these functions have is that if you take this first quadrant graph and flip it to the left, and then flip it one more time over to the x. So if you reflect the graph over the y-axis and then the x-axis, which is same thing as saying that the graph is reflected over the origin. And it's still the same thing as saying that you take this graph and rotate 180 degrees. You rotate it, you don't flip, you just rotate it, then it's the same graph as before. Okay? Now, if you have a graph that satisfies such a thing, you call this function an odd function. Right? The name comes from the fact that at least for polynomials, these are odd powers. Okay, so it's an odd function. And the behavior of these functions can again be expressed by these hand signs. Like this will be the it's this one, yeah. So this is the odd power function, right? Get it? Okay. Now, once you figure these out, then we're going to put numbers in front. Now we're going to put numbers in front. What is the end behavior of negative 2x cubed? Think about this. So you have y equals to x cubed, which is this. Now what does y equals to 2x cubed do? This just stretches this way, right? So the graph still looks somewhat same. It's still this way. What does the minus do? If you put a minus in front, what would it do? Come on, you know this. Flips it, right? It flips upside down, right? So minus 2x cubed, that's like that. Okay. Therefore, what's the end behavior? It's this, right? Okay, that's the end behavior, right? So you should be able to think about the end behavior of these power functions by either this or this or this or that. So they're basically four choices, right? And knowing that actually helps you to draw the graph. That we're going to be doing polynomial graphs a little later, and you have to know the end behavior in order to draw that graph. Okay, let's just do one more. So suppose you're given y equals to negative 7x to the sixth power. What's the end behavior? First, if you just had x to the sixth, what's the end behavior? It's even, so it's this, right? I don't care about 7 because it's all it does is stretching, but there's a minus, so what do it do? So it'll be this, all right? Okay? All right, so that's the end behavior. All right, good.